In this video, we approximate the zeros of this particular function using Newton's method. I think we all know what the zeros are in terms of radical expressions. We just set the y value equal to 0. And then solve for x. So x cubed equals 2. So x equals the cube root of 2. But I don't actually know what the cube root of 2 is without my calculator. So we're going to use Newton's method and continue to use Newton's method until the difference between two successive approximations of this 0 is less than 0.001. So that's the plan. We know that the 0 is this. We'd like to approximate it, and we'll use Newton's method to do so. So, well, one way that we can do that is we can graph the function. Y equals x cubed looks like this. Now, if we multiply by -1, that's going to flip this. All these negative values are going to be positive, and all these positive values will be negative, and then we'll shift the whole thing up 2 units. So when x equals -1, we're going to have 2 minus a -1. -1 cubed is -1, so we're subtracting. We have 2 minus a -1 cubed. -1 cubed is -1. 2 minus -1 is 2 plus 1, which is 3. And then at x equals 1, we've got 1 cubed, which is 1. 2 minus 1 is 1. And so our graph is going to look like this. And then at x equals 2, the graph is, or the y value is 2 minus 2 cubed. 2 cubed is 8, so we have 2 minus 8, which is -6. So you say, okay, if I know that my point passes through x equals 1, y equals 1, or my graph passes through x equals 1, y equals 1, and my graph passes through x equals 2, y equals -6, then I know that the function has to have a 0 between x equals 1 and 2. I just like to find out what it is. Well, it turns out that it's the cube root of 2. Say, well, how can I find that numerically? Well, one way that we can find that is we can find a secant line that passes through those 2 points. And then we can say to ourselves, okay, I bet the x-intercept of that secant line is very close to the x-intercept of that actual function, the x-intercept that we're looking for. So we will find the secant line, find its x-intercept, and then we'll use that as our approximation of that 0 that's between 1 and 2. So we'll do that first. So the slope of the secant line is f evaluated at 2 minus f evaluated at 1 divided by 2 minus 1. F evaluated at 2 is -6. F evaluated at 1 was 1. So our slope of our secant is -7. And then the secant line has this equation. It's y equals the y value at x equals 2 plus the slope of the secant, which is -7 times x minus 2. We could have just as easily used x equals 1 here. We'd have f of 1 and x minus 1 in that case. The line passes through both points, so we can use either point. F of 2 is -6. Slope of the secant is -7. If we distribute that -7, we get this. And 14 minus 6 is 8. So you have -7x plus 8. So that is our secant line. You say, okay, well, how does that help us? Well, the first guess for our 0 of the cubic function 2 minus x cubed is the x value that causes this function to be 0. So we'll set y equal to 0 and solve for x. So we'll subtract 8 from both sides. We'll divide both sides by -7. And we'll have x equals 8 divided by 7. And we'll say that's our first guess. Our first guess will denote by x naught. And I actually don't know what that is approximately. That's going to be some number. Now, if we evaluate the function at that number, that's f of 8 divided by 7, we have 2 minus 8 divided by 7 cubed. Oh goodness. Actually, I don't know what that number is. We have 2 times 7 cubed minus 8 cubed, all divided by 7 cubed. And I don't know what that is without a calculator. So maybe I can't use Newton's method without a calculator. 7 times 7 times 7 is 343. We'll multiply by 2. That is 686. Then I'm subtracting 8 times 8 times 8, which is 512. And I'm dividing by 7 cubed, which is at 343 again. I have 686 minus 512 is 174. And we're dividing by 343. And with the sign or with the calculator on my phone, I get 0.50728. So x is approximately 0.5072, and then I'll just estimate that to be 0.50729 approximately out to the 5th decimal place. So that is our y value there. And this 8 divided by 7, I can use my calculator for that as well. It's 1.14285. So we'll say that's approximately 1.14285. I'll round up to 86. So that's my x value, my first guess, and that's the corresponding y value. Say, okay, now that I have this as a guess for my x value, I can iterate again, and I'll find, but this time instead of using the secant line, I'll actually use the tangent line at this x value, because I'm pretty sure that that x value, or that x-intercept of that secant line is very close to the x-intercept of the original function. So then I just use the tangent line at the x-intercept of the secant line as my next, to find my next tangent line. And then we do that again. So we have the tangent line, the next tangent line for x1 is y equals f of x naught plus f prime at x naught times x minus x naught. And that's approximately 0.507, right? Oops, I can't see my paper. Plus the derivative at x naught, I don't know what that is, minus 1.14286. I'll just round out to the 4th decimal place, so I'll do 29 there. And that, if I'm going out to the 4th decimal place, that should be a 3 after the 7. Now, in order to do that, I need to plug this x value into f prime. Now, f of x was 2 minus x cubed. So f prime of x is negative 3x squared. So we need to evaluate that negative 3x squared at this x value. So we have f prime of x naught is negative 3 times x naught squared. So it's negative 3 times 1.1429 squared. And I'll use my calculator for that. $1.1429 times 1.1429 times 3 is approximately 3.9187, and it's negative. So our y value is approximately 0.50728. 3.5073 minus 3.9187 times x minus 1.1492 or 1.1429. And then if we distribute this times this, I know it's kind of tedious. 0.9187 times 1.1429. When I multiply those together, I get this value, 4.4787. And then these are like terms, so I'll add those together. 4.4787 plus 0.5073. And so I end up with negative 3.1987x plus 4.986 as the tangent line at x equals x naught, y equals f of x naught. Now, in order to find x1, I'll set the y value equal to 0 here and solve for x. So we have 0 equals this value, or equals this. And the solution of this equation is what I'll call x1. So x1 is negative 4.986. And I was going out to 4 decimal places, but I didn't have 4 decimal places this time. Divided by negative 3.9187. And I get approximately 1.2723 as my x value. And if I compare x1 and x sub 0, that's 1.273 or 1.2723 minus that 1.1429. I get a difference of approximately 0.29. So we're not close enough yet. So what we want to do is we want to find that tangent line again. So to find x at x2, that's our next guess, we'll find the tangent line at x1. So we'll find the y is equal to the original y value at x1 plus the slope at x1 times x minus x1. And x2 is the solution of this equation when y is equal to 0. So we'll have 0 here and we'll have x2 here. And if you subtract this from both sides, got that. You divide both sides by f prime at x1. Have that. And you're trying to get x2 by itself. So x2 is x1 minus f of x1 divided by f prime at x1. And x1 was approximately 1.2723. The function value at x1, I didn't evaluate that, but it's going to be 2 minus x1 cubed. And then we'll divide by the derivative at x1, so that's negative 3 times x1 squared. So we usually let the calculator or the computer do that calculation for us. Just a bunch of arithmetic. So I have 1.2723 times 1.2723 times 1.2723. And we're going to subtract that from 2. And so I would have this value but negative. So I did it backwards. And then we're dividing by this -3 times 1.2723 times 1.2723. And so I have a -4.8562 there. So the new x value, x2, is this minus this number. So we'll do 1.2723 minus 0.05953 divided by 4.8563. And I get approximately 1.2600. So that's my x2. And then I'll look at the difference between x1 and x2. So we've got the absolute value of 1.2600 minus 1.2723. And so we're going to get 0.0123. So the difference between the successive values is a little bit more than 1/100th. So we're not quite where we want to be yet. We're trying to get that difference to be less than 0.001. So we do this again, x3. We have y equals f at x2 plus f prime at x2 times x minus x2. And then we set y equal to 0. And we say that this x is actually our x3. The x value that solves this equation is called x3. Then when we're trying to get x3 by itself, we subtract f of x2 from both sides. We divide both sides by f prime of x2. And then we add x2 to both sides. So we have x3 is equal to x2 minus f of x2 divided by f prime of x2. And x2 was approximately 1.26. So then we'll subtract 2 minus 1.26 cubed. And then we'll divide by f prime at x2, so that's -3 times 1.26 squared. So that's just my function evaluated at x2, and that's my derivative evaluated at x2. You can see how tedious this is. That's why we usually have a calculator, or rather a computer, do it. So 1.26 times 1.26 times 1.26, that minus 2 is 0.000376. That's in my numerator. And we're going to divide that by this 3 times 1.26 squared. -3 times 1.26 times 1.26. So 4.7628. So it's a very small number. So I have 0.000376 divided by 4.7628. And actually, this should be minus. Because when I distribute that negative, I have this numerator, and then we still have that negative from the denominator. So we're going to have 1.26 minus this answer. So I'm just going to subtract 1.26 from it. It's going to give me the wrong sign. That's okay. So my value is actually approximately 1.2599. And then the difference between x3 and x2 is the difference between 1.2599 and 1.2600, which is 0.0001. And I think we were trying to be less than 0.001. And so our difference is less than 0.001 now. So we'll stop and we'll say that this is a good approximation of the 0. Now I would like to compare that value to the cube root of 2 because we know that that's our actual answer. Let's do that on the computer now on Desmos.com. So we have this function, we see that this is our 0, and we're trying to approximate it. And it's kind of hard to get to. Approximately, well, it's 1.26 is what Desmos says is 0. Now, if we have a grid, step size of 1, so let's get rid of the grid. We can see that the 0 is between 1 and 2. So we said, let's evaluate f at 1 and plot the point. Actually, I want to use that color. I think it's prettier. And then we'll evaluate that function at 2 as well. And we see that the y values go from positive to negative. So we definitely have a 0 there. The function is differentiable and continuous. So by the intermediate value theorem, there is a 0 on this interval. And one of the best ways to find it is to find a secant line that passes through those 2 points, and then find the x-intercept of that secant line. So first we'll find the slope of the secant line. That's just going to be f of 2 minus f of 1, all divided by 2 minus 1. So we've got a slope of -7. And we'll let y equal the y value at 1, which is 1, plus the slope of the secant line times x minus 1. And so we see that that secant line and the original function have an x-intercept that is very, very close to each other. So if I want to find that first x value, or that first approximation to that 0, I set the y value on this tangent line equal to 0 and solve for x. So I've got x sub 0, that's our first guess, is, well, if I have a 0 here, I'll subtract f of 1 from both sides. I'll divide by the secant slope, and then I'll add 1. So I'll have my first approximation to the x value is 1.1428, which is what I got on paper. You say, well, that's not good enough. Let's plot that point on the graph of f. And then graph the secant line there. We could also plot that point on the x-axis if we wanted to. You can say, okay, that's the point. It's close to the x, or the x-intercept that we're looking for, but we're not quite there yet. So let's find the secant line, or excuse me, the tangent line at x naught, f of x naught. So we have the next tangent line is y equals f of x naught, or the last time we used the secant line, now we're going to use the tangent line, plus the slope at x naught times x minus x naught. And if we zoom in, we can see that the x-intercept of the graph itself and the x-intercept of the tangent line are very similar. To find that x-intercept, we'll solve this for x, we'll call that x sub 1, and we'll set y equal to 0. So we'll have 0 minus f of x naught is going to be negative f of x naught. Then we'll divide by the slope at x naught. And then we'll add x naught to get x1. And so we have this as our x value. Now, if we look at the absolute value of x sub 1 and x sub, or minus x sub 0, we see that the difference is pretty large, larger than we want. So we want to iterate again. Let's find another tangent line. At x sub 1, f of x sub 1. So we'll have y equals f of x sub 1 plus f prime of x sub 1 times x minus x sub 1. We'll solve for x, we'll call that x sub 2. When y is 0, so we have negative f of x sub 1 minus f prime at x sub 1. And then we'll add x sub 1 to both sides, and that'll be our x sub 2. We'll say x sub 2 is this value. And that looks really close to the y-intercept of the function. Like I can't even tell the difference between the tangent line and the original function value there. They look almost identical as we get close to that 0. So we know our 0 is between 1.2 and 1.4 now. We just don't know exactly what it is yet. Let's evaluate the function at x sub 2 and see what Desmos says for the value. It's saying the y value is negative 0.0006. We wanted the y value to be 0, but it's not 0 yet. So we will iterate one more time. Just find the equation of the tangent line at x2. So f of x2 is our y value, and then we have the slope at x2 minus x sub 2. And then x sub 3 will be the x value that causes the y value in this graph to be 0. So we'll have 0 minus f of x sub 2 divided by f prime at x sub 2. And then we'll add x sub 2 to both sides. And so we'll have that as our x sub 3. And then if we look at the absolute value of x sub 3 minus x sub 2, we say that is definitely less than 0.001. It's 1/10,000th as opposed to 1,000. So we're going to call this x sub 3 the root of our function. And if we zoom out and say, let's plot x sub 3 and f of x sub 3 now. They're calling it 0. So we're saying that is the root of the function. So that's Newton's method. Now, if you want to, you could just use this formula over and over again, but I want you to know where the formula comes from. It comes from finding those tangent lines and then setting the y value equal to 0 and then solving for x. And then we're saying that particular x value for that particular tangent line is the next x value. So if we use the tangent line when x equals x2 to find the next x value, the solution to that equation when y equals 0 is going to be called x3. In general, we'll have x sub n here, x sub n here, and x sub n here, and x sub n plus 1 will be the solution of the equation when y equals 0. So we'll have x sub n is equal to the last x value minus the function value at the last x value divided by the derivative at the last x value. As we keep using this formula over and over again, because the form of the equation of a line is always the same. But that's Newton's method. Now I'd like to compare that to the cube root of 2, because I know that that's our exact answer. So the cube root of 2 is this, and then x3 was our last approximation. So we have a 1.2599216, or 2106, and this is 1.259921049. So we are actually the difference between x sub 3 and 2 to the 1/3, like our guess and the actual value of the root, is on the order of 10 to the negative 8. So the 1, 2, 3, 4, 5, 6, 7 digits after the decimal point are all correct. The 8th digit is the only one that's off by a little bit. It's supposed to be a 4 and then a 9, not a 6 and then a 1. So that's our error. I would say we did pretty well, and we only had to go out to x sub 3. So we had x sub 0, x sub 1, x sub 2, x sub 3, and then our answer, or our guess, was within 10 to the negative 7th of the actual answer. So our answer was accurate out to the 7th decimal place, which I think is pretty impressive. So that's Newton's method.